And we'll turn it over to you guys.
Okay, well, hello. I would just like to thank you for attending this morning. So our company is Tremors and we are group 635T. And today we are going to present to you our shaker table design. So our members consist of Megan Davis, Hayden Matson, Nate Keys, Katie Laura, Lance Herlong, Giovanni Gorgati, and Jaren Palmazan. All right, so for our presentation outline, these are going to be some of the topics that we are going to touch on throughout the presentation. And first, we're going to touch on the hedgehog. So for the hedgehog concept, we felt that our design had a good leverage compared to other teams because of other members' mechanical design experience. Our main goal was to develop an efficient, simplistic design while also minimizing the cost. Efficiency was deemed to be the most important because to drive efficiency, cost is an important aspect to recognize. So to do this, we wanted our design to mostly implement OTS parts with very minimal machining necessary, and any machining needed was to be simple. So going on to more general specifications about our shaker table, we were able to implement 3 patterns being linear, orbital, and double orbital. We also included space in our design for future teams to implement a ODFI system. We made sure that a factor of safety of 1.5 is achieved throughout the system, which will help minimize failure while also maintaining an operational lifetime of over 5 years. Additionally, we implemented a maximum speed of 300 RPM by using coding to control the intervals of the motor rotation while also tuning the motor driver current regulators. We included an external controller with an intuitive user interface to be able to control different patterns, RPM, and to also turn on and off the table. We further included emergency shutoffs and fail safes by implementing limit switches, which we're going to further discuss later on in the presentation.
Yeah, so our design uses a linkage bar system. These linkages utilize steel bearings that are press fit and connect to 2 offset motor hubs. These motor hubs have different distances from the center of the motor that they can attach to that allows for different orbital links and distances that it can move when it's operating. And go to the next slide. This system allows us to move in any direction that we choose. We can go to an orbital pattern, which has both motors orbiting in the same direction at the same speed. Linear patterns that go in the same speed in opposite directions, and then they can also go to a double orbital, which can go where one goes at 1 speed, the other one goes at twice the speed in order to reach that pattern.
Our shaker table also features an external control box to be housed outside of the microbioreactor. We're using an Arduino Uno microcontroller to kind of serve as the brains of the operation, as well as a voltage regulator to step down the voltage from 12 volts to 5 volts. We're also using 2 NEMA 17 stepper motors driven by 2 A4988 stepper motor drivers to actuate the motors to actuate the motion of the shaker table. We're also using a Rotary Encoder push button along with a 16:2 LCD display module to create that intuitive user experience for the customer, as well as 2 bipolar Hall effect sensors to create a sort of homing sequence for the shaker table, as well as 4 limit switches to kind of act as emergency stops in case the shaker table does not actuate as intended. So as I mentioned before, the Rotary Encoder push button is used in combination with that LCD display module to create a simple user experience for the customer. The original motivation for using this single button to kind of control the whole table actually started with us trying to just reduce the amount of inputs we were putting into the Arduino, but it actually ended up making huge strides in terms of simplifying the user experience. So now pretty much all the user has to do is kind of initiate a short press of the push button to change the shaker table pattern, turn the encoder to change the RPM at which the shaker table will actuate, and then hold that push button for longer than a second to begin the starting sequence. And that is all programmed in sequence with the LCD display module so that the user kind of knows what's going on behind the scenes.
So one key part of our table that we focused on is the safety aspect, because obviously if this is going into mass production, we want to make sure the customers are safe when they're using our table. So first of all, we have a very low center of gravity. And this allows our table, along with the rubber feet that are attached to the bottom, to be really stable. And stability in our actuation system means that it's further reduced chances of failure. We also have physical stoppers at the end of each rail. So normally while the system is actuating, the slide bearings should never touch the end of the rail. But if something did fail and the slide bearing does happen to reach the end of the rail, those physical blocks would stop it. Also attached to those blocks, we have limit switches. And the limit switches, when triggered, will stop the actuation system of our table. And then our final kind of fail-safe safety feature is on the actual external controller, our stop-start button. If someone was operating the table and they notice something wrong, they're able to press the button on the external controller and the code would stop the shaker table from actuating. So then as far as our table goes, we had to run our table at maximum speed for each test. While our stepper motors are rated for 600 RPM, between the coding processing through our electronics and through the stepper motor driver current regulators, the maximum speed we were able to reach was 300 RPM. Now Jaren will talk about the testing results.
So for the endurance test, or for our torture testing for our shaker table this semester, we did 3 different endurance tests. So the first endurance test that we performed was a linear pattern. And with the linear pattern, we were able to successfully get 55 minutes of continuous runtime with the pattern still looking, linear. However, we did, on our first attempt of this test, one of the linkage arms snapped. And so later we'll talk about the mechanical evolution of that linkage arm to succeed. But once we sort of thickened up that linkage arm, we were able to successfully output a linear pattern for 55 minutes without a single bat of the eye. Furthermore, the orbital pattern. So with the orbital pattern, it was by far and large the smoothest pattern that we were able to run. With the orbital motion of the table, the inertial forces sort of were dispersed all around the table, and that reduced the vibration of the system immensely. And as such, we were able to reach 2 hours of continuous smooth runtime while still operating with that perfect circular pattern. In contrast, if it will load. In contrast, we had the double orbital pattern, which compared to the orbital pattern was our least smooth shaking pattern. So although our goal was to reach 55 minutes of continuous runtime in this double orbital pattern, we ran it for the minimum runtime of 20 minutes because we didn't want to have the system fry after we just got it to work. So we hedged our bets and just once we reached 20 minutes of successful runtime, we called it. And that's about it.
So as we mentioned earlier, there were lots of mechanical design evolutions on our shaker table. First and foremost, before we even began some of our testing, we eliminated a couple manufactured parts just to further streamline the design, move more towards our priority of OTS parts, something that's easy to manufacture. So some of the parts that we eliminated were the sheet metal enclosure that would have encapsulated our entire design. Again, this is more of a prototype phase. We were doing a proof of concept and then developing a shaker table. And we felt that this was a part that we were able to eliminate while still not compromising on any aspects of the shaker table. The second part that we ended up modifying was our well plate test tube holder. So the original design was a sheet metal design intended to hold one of the standard well plates. But after looking around at some of the other test tube racks and test tube holders that were provided for us in our box, we decided to come up with a lightweight 3D printed solution that was able to hold both your standard well plate and test tube racks of various sizes. So this also reduced the inertia and the overall mass of the part of the shaker table that is shaking, which in turn reduced some stress on the motors and linkages. And then, as we mentioned earlier, we did have a mechanical failure of one of the linkage arms. Originally, when these linkage arms were designed, they were intended to be aluminum manufactured in lab. But after doing some calculations, we realized that these linkages could be 3D printed. They would still withstand all the stresses that our shaker table would afford on them. So here you can see that even though our initial math, which we will go over, proved that we could use these linkages based on the properties of PLA, we ended up having to increase the size by 50% on that stress concentration area so that they no longer fractured right there. So moving into a little bit of that linkage arm redesign, you can kind of see the cross-sectional area, new versus old, in that part that's highlighted in the picture. So our original design had a 20% infill. It was made with PLA, and we had all of our justification there for a factor of safety of 5. So we kind of went in circles over and over again as to why we thought this was failing. But overall, when we were coding the table, when we were running through different test iterations, the motors were jerking around a lot, yanking on the linkages. We had a lot of orbit patterns that weren't meshed up with exactly linear orbital or double orbital. So there were a lot of stresses induced on these linkage arms through the testing and prototype development process that we may not fully have encapsulated here in our initial design. Additionally, these are based on the ideal properties of PLA in terms of tensile strength. And overall, printing these linkages on my 3D printer, we saw at the fraction points, even when this linkage failed catastrophically, there were smaller stress cracks on some of the other parts of linkages, just showing that there was imperfect bonding of layers within the PLA 3D printed part. And you can see where, even though in an ideal world, PLA may have a tensile strength of between 26 and 32 megapascals, we do not believe that was accurate for the case of our 3D printed arms. So therefore, we increased the size of the area and we increased the size of the infill to have an even larger factor of safety. And since then have not seen or experienced any sort of stress fractures, or breakages on the linkages.
So there was also a design evolution on the electrical side of our shaker table as well. The primary one being the implementation of a homing sequence for our shaker table. So something we kind of noticed in the early prototyping phase is if both of our motors didn't actuate from a very specific starting position, it wouldn't quite reach orbital, it wouldn't quite reach linear, it wouldn't quite reach double orbital. So it was pretty important that we kind of set a ground zero for our motors to be actuating at, and that's where the Hall effect sensors came in. So the way that we implemented the Hall effect sensors into our shaker table was first by setting some tiny little magnets on the side of each of our motor offset hubs, and then mounting the Hall effect sensors really nearby. So how this works on the software side is that essentially as soon as somebody holds that button, it initiates the homing sequence. And what the code is looking for is simply a change in state of the Hall effect sensor, which is reflected visually by that red light turning on and off. So again, what that does for us is provide a ground zero for our motors to begin actuating at, to make sure that we do have an accurate orbital rotation, linear rotation, or double orbital rotation. And it also allows for our motors to stay in sync as they rotate together.
So moving on to some photos and little illustrations that demonstrate the CAD of our entire design. You can see many of the design features that we've talked about throughout this presentation, whether it be the low center of gravity, or as demonstrated on the left, how the shaker table functions using a solid versus motion study. This is also how we're able to validate different ideas, such as depending on the orbital, would we have any sort of interferences, making sure that our linear rails we're not getting too close to the edges, and just validating all of our different design parameters. And then I also wanted to touch on, with the CAD overview, our actual linkage system. So we discussed it a lot earlier, but we spent a lot of time making sure that our design uses as much OTS parts as possible, specifically for this section. So while there are, a dozen pieces over there on the illustration on the right, the only parts that are custom manufactured are the linkage arms, the central pivot, and then the motor hubs. These motor hubs and linkages are identical, so you don't have multiple versions of the same part. They're all the same. They're also extremely easy to manufacture. Both the central pivot and the motor hubs can be made on a manual lathe. They don't require any CNC work. They're very simple parts with easy to work with dimensions. And then, as we mentioned earlier, the linkages themselves are 3D printed, so those are very easy to manufacture. Everything from the bearings to the washers to the inserts and the fasteners, these are all OTS. So as we mentioned earlier, if customers had any problems in the future, a lot of these parts would be very easy to switch out, very easy to remanufacture. So just overall, this linkage system really prioritizes as many OTS parts as possible So even from the early stages of prototyping, we're able to very quickly create a working prototype of this linkage system and then dive right into the coding aspects, which for our group proved to be much more difficult. Another thing that I wanted to highlight on this slide, you can see it in the picture on the left, is that the motor actuation linkage system is completely independent from the rest of the table. So before we even have this linkage system hooked up, we could show our top plate on the shaker table hooked up to all the linear slides, and you could manually move the linear table around in any way you'd want before any sort of motor actuation. So that whole motor system and the linkages are completely independent from the linear slides. And this means that if either part of the design were to change or evolve in the future as other groups took on this project and dove into what we've done, they wouldn't have to reinvent the wheel. Each part is completely independent, synced up at the last minute.
So to talk about cost, the cost for a single prototype, the total was around $375. And that was calculated, as you can see, with several different sections. We found that because our shaker table is mostly comprised of OTS parts, that was the majority of our cost. And then the assembly time that we found was 16 minutes. And that was assuming that one person was working on the assembly using the Boothroyd and Drewhurst chart. And we found that the manufacturing time was around 5.5 hours. And then having a cost of $18 an hour per worker, that was around $99 for the total manufacturing time. And then on to the next slide, I can talk about how these costs change a little bit when the shaker table is mass produced. So as you can see, the OTS parts and raw materials had a significant decrease in cost. And that is due to us purchasing a lot of these materials and parts in bulk, now that we are mass producing these shaker tables. And the assembly time, we actually kept the same. Again, using the Boothroyd chart, we found that it'd be around 16 minutes, and that was a total of around $4.50 for the assembly. And the manufacturing time was also dramatically decreased to around 1 hour, because now a lot of the steps in producing these parts would be automated rather than more manual labor that was involved in a single prototype. And the cost was reduced to around $213.
Oh yeah, so for future design, so all of this is capstone, that's in your capstone, but we know that this was intended for future teams to pick up and work with and implement, new features to work with their designs for the other components of the shaker table. So one key thing that we need to add into our design is more adjustable orbital radii. So as of now, we have 2 slots on our motor offset hubs that allow us to adjust between 2 linkage settings, so 2 different radii. In the future, it would be ideal to have small increments throughout those 2 hubs. So that'd be something great for the next team to pick up on. Furthermore, more precise RPM control would be perfect. So as it stands now, we can go from 50 to 100, 150, so on and so forth, up to 300 RPM. So being able to capture those in-between RPM values is, essential for having a shaker table that can perform exactly what you want. And then finally, when we were doing the endurance testing and while we were prototyping throughout the semester, we noticed that anytime we were using these NEMA motors, the motor drivers themselves would get really hot to the touch, insanely fast and insanely hot. So when we were running the endurance testing, we were a little worried, like, how do we not fry everything the second we start testing? So we brought in a fan. So although we used a fan in our endurance testing, we did not have that hooked up to our perf board. It was just there actively cooling. So in the future, we would need some sort of active cooling component in this bioreactor system or just the shaker table system to ensure that the components, specifically the motor drivers, are not getting too hot.
So to summarize why we think our shaker table is competitive versus other shaker tables, our use of mostly OTS parts gave us a huge advantage, especially in prototyping. We were able to order all the parts the first week, and then by a week after they came, we were able to have a functional mechanical system, and then we were able to work on the electrical and spend more time on the coding and developing the different dynamics for our actuation systems. Using OTS parts also made our table a lot more affordable because, as we said before, manufacturing parts, custom parts costs a lot more. It takes manufacturing time. So we were able to eliminate a lot of that by using OTS parts. And then generally the assembly time was very low because a lot of these parts didn't have complicated geometry because they weren't custom. And finally, using OTS parts allows the customer to easily repair broken parts because they can just order a new one instead of having to remanufacture a custom part. So that's why we think our table is very competitive against current designs.
So thank you for joining us, and now it's on to any questions.
Okay. Awesome. Thanks, guys. So my call for more evaluators was answered by basically the entire teaching team. So so we've got Alex, Javian, and Juliana have popped in. I don't know if there's anybody else. No. Okay. Yeah. So now you got the four of us. I don't know if it was better before or now, but here we are. So let me first ask if any of the other panelists, Alex, Javian, or Juliana, have questions before I jump in with mine.
Hey guys, I just wanted to apologize firstly for not being in earlier. I meant to come in right at 10:40, but just I'm all over the place right now and totally lost track of time. But I just wanted to compliment the foresight and understanding that it's very difficult to do calculations, nearly impossible to do like standard mechanics of materials calculations on 3D printed parts because they don't exhibit uniform geometry. And, the naive engineer would just do that calculation and accept the result when in fact you really just can't because of the non-consistent geometry throughout those planar cross sections with the layers. So I just appreciate when people think about that.
Thank you.
Okay. Any other? Sorry, I'm fighting my cat here. I should have had the speaking
Show
of
the cat.
foresight. I should have had the foresight to put this thing out because now she's decided that this is her favorite place. Okay, she jumped out. Okay, any other?
So unfortunately, I couldn't see the whole presentation. I joined in late. But the thing that I've seen looked really good, and it sounded like you were confident in what you were saying and knew what you were going to say. So that definitely places a good, let's say, impression on everyone in there who's watching. So good job.
Thank you.
Thank you.
Okay, so
Yeah, I absolutely agree with that.
oh, okay.
Awesome, thank you.
All right, so okay, I guess I'll jump in with a couple of questions. So were there any other groups that did the two rotating motor double linkage design that you guys showed?
Yeah, there was one other group that did a very similar aspect of ours. Ours were in different orientations. The motor hubs were. Ours were more like in this orientation, and theirs was more in the XY orientation.
Yeah.
I
But
don't know which group it was, but yeah.
But everyone else did belts and pulleys and
Pretty much. Yeah.
separated
Yes.
linkages. Okay, so I'm not sure that it was your group, but so Dr. Nemi came to me at like maybe a day or two ago, and he basically said there's a Mech 3 team that feels like you threw them under the bus. Because there were, and again, I don't know if this is you guys or someone else, but because they're working with an actuation mechanism that's basically different from everybody else, and it's not working nearly as well as the belts and the separated linkages, and they pursued this thing because they felt like you wanted them to do it, and now they're feeling sort of immense frustration and feeling like they should have gone a different route. And I don't know that that's you guys because he didn't tell me which group.
Yeah, it wasn't.
Oh,
I don't believe so because both of these designs that work off of this principle actually function incredibly well.
yeah. Well,
And I know the group.
so that's sort of where I'm going with this. That's why I asked how many other groups did this thing, because I was trying to sort of suss out whether you guys were the ones that he was talking about without like revealing too much. But so so I have too many thoughts and now I can't think of the one that I want to say. So there was a time, and some of you might even be of this vintage, the first time that we made the microbioreactor project, the project in MEC2, we actually had more than one group that like on recorded video in front of the entire, design community, UF, basically said that it was impossible to do linear orbital and double orbital patterns on the same like shaker table. Like they were like, we've done the math and it's impossible, it can't be done. And more than one group said that to me. And it was the end of the semester and they were stressed out, and it was the first time we'd ever done it, so nobody had actually gone through the kinematics to kind of figure out like how it would work. But so I guess first thing is I'm from that start of actually having students, not you guys, but having student groups tell me that this is impossible. The fact that you made it possible and to use Alex's words, functioned extremely well, was very impressive. The thing that I want to ask though is so given that it was just you guys and one other group and everybody else was doing like linkages and belts and all these other things, which probably were quite a bit easier to implement and required a lot less like, programming and math and coordination. How did you guys feel as you're looking around and watching all these other groups basically take the easy way and you guys are doing this much harder thing?
I mean, I feel like we thought our mechanical design was pretty good. Like it just made sense to us.
Yeah.
Like the system, Hayden kind of based it off a lot of the independent study and some of the other works. And, we tested off in SolidWorks, we could get the patterns working. I think our hardest, battle this semester was the coding and some of the perf board mishaps, but like, we were pretty confident in our design, I would say.
Yeah, I would say that. for
Yeah,
sure.
I would say for me, a lot of I think I spent half the semester feeling more like a computer engineer than a mechanical engineer, especially since, all we had going into this was baby circuits, and in baby circuits, you don't quite do a lot of coding. The coding is given to you and you're expected to understand it, but you're never like developing code. So I think this was the first time in our curriculum where we were formally developing Arduino code, and that was pretty difficult because it's nowhere near the same logic as MATLAB. Because if you look at our code, it's more like function based, and like functions aren't normally something I found myself to be implementing in MATLAB throughout my coursework here. So.
And definitely we felt that like linear, like as far as dynamics wise with our actuation system, linear and orbital were super easy and like really intuitive for us to figure out. And then the double orbital, we spent so much time trying to figure out the double orbital, and then we just eventually right before testing just got it to work. And we're like, oh my God, it's a miracle.
Like literally minutes before we left.
Yeah.
I will say that's a lot more overthinking than it is anything.
Yeah.
It ended up being actually super simple.
Yeah.
Yeah,
So,
it definitely came in waves. We had moments where like, oh, we got this is great. And then when double orbital came, we were all really struggling and stressing out until we finally got it. And then we were back on that high horse, like, oh, we got this. Like, oh, this is a solid design.
Yeah, and kind of to the same point, we were, I guess, 2 weeks after the first order date was put in, and we were able to put almost all of our manufactured parts in the queue the first week and have them completed in the manufacturing time. So we were like 2.5 weeks in, and we basically felt like we had an entire shaker table built. We had the slides, we had the linkage system. We're like, okay, sweet. Now we just got to program it. And that was the hard part. Exactly.
Great. Okay. Yeah. Well, so based on, just nothing technical, just kind of, intuition, as I look around the room and see all the various designs, I'm convinced that the configuration you guys came up with is the best one, is the right one. All these belts and linkages, because you guys, your motors rotate all the way around, right? They don't stop. And yeah. See, we've got, well, I guess when you run yours, how loud is it? Like, is it quiet?
It's quiet.
It's not, it's not that loud.
Yeah. See, that's another thing is there's all the teams that are doing like the motor reversals, their shakers are so, and if this is recorded, so to everybody else out there, I'm sorry, but your shakers are really loud, like, and they probably would never actually be successful commercial products. Not you guys. You guys are so I think like what is I think excellent about what you guys figured out is that you don't have to do any motor reversals, and yet you still have, without making any, like mechanical changes, the ability to hit all three patterns. And it's that combination of like being able to hit all three patterns and no motor reversals. And then like there's only like one linkage, right? And of course, you guys had the unfortunate situation where yours broke. But a lot of these other designs, there's just too many parts, and lots of failure modes. So for what it's worth, right? I'm not a shaker table guy, but I really feel like the design that you guys came up with is like the right one for this particular set of customer needs, and for possible commercialization. So I want to applaud you for that. I mean, it sounds like you guys were very confident the whole way through. So you're probably not the group that Dr. Nimi was talking about, but yeah, I thought that might've been you guys. So yeah, I wanted to, just say that I really like the just sort of two linkage orbital like that. That's, I think, the best design. I guess, now my cat's breaking the shelf. Dear God. Okay, well, we'll let her do that because, so I guess the other thing that I wanted to ask was the pictures that you guys showed of the like the conical tube holder, that was the off the shelf one that we bought for you in the beginning.
Yes.
Is that right? Okay. Did you guys end up like designing a different one, or you're using that one as like your suggestion for this is the permanent version of this for next semester?
Yeah, we were using the off-the-shelf one that you provided to us, and we just made that 3D printed mount to hold it. We also figured that, in the future, when the ODFI system gets implemented, that future group is going to be able to take the bones. So we're just saying, hey, look, you've got plenty of space within this area. We had pegs that held the entire test tube rack up to give space for an ODFI system. So in the future implementations, when they start adding that stuff in, they'll be able to kind of take that idea and run with it.
Got it. Okay. All right. And then can you guys go back to, you had a linkage failure slide somewhere. No, further back than this. I also, just as by way of another compliment, I really like that I know you guys didn't actually build the enclosure, maybe you did, I don't know, but I really like that you show pictures of the CAD model with like the final enclosure. There's a lot of groups. If you guys remember back to in the beginning of class, I was adamant that this thing actually looked like a shaker table, and have an enclosure and actually be, at least have the appearance of a commercial product. And I think a lot of groups kind of forgot that. So I appreciate that you guys are showing lots of pictures, at least in CAD, of the design in its final form as a commercial product with the enclosure on. Because I think that's, again, like imagining that this is a commercial product, I think that's a good way to present it. Okay, yeah, this is the slide that I was, okay. So you guys talked a good bit about this, and I think I'm following what happened here, which is you guys did, had this part not been 3D printed, this would have been just a mechanics and materials. In fact, I think that's how you guys treated it, right? You guys did the analysis based on mechanics and materials, stress concentration, and you found that had this been a monolithic part, not a 3D printed part, that it would have survived.
Right.
Okay. And then and the reason I gather that it did not survive, kind of following up on what Alex said, is there's not 100% infill in this part.
Correct. And we adjusted our calculations where we did 20% infill. So we did 20% of the area. And we still got that it should survive. But when you actually looked at and I know it's kind of hard to see in the picture, I'm sure on Zoom, but when you look at the failure point, you can actually see where each layer of the 3D print kind of failed individually and they were separating. So, it wasn't that it just, exceeded the maximum tensile strength of the PLA, just snapped. It was that, those stress concentrations were forming on specific points of the 3D printed layers. and they started separating. So we were thinking, it's more of it's like Alex was saying, it was more of a 3D print design failure, as opposed to necessarily the PLA's properties or the calculus we had gone into. We just didn't take that into an account.
Yeah, I got you. 3D printed stuff is weird. So, okay. And then you say here, I'm reaching for a mouse that I don't have. Well plate mount 3D printed rather than sheet metal. So your solution to this was to just 3D print like a bulkier linkage, right? Is that
Yes.
okay? And is that so when you guys go into like commercial, let me maybe ask a different question. Well, no, same question, but with a different spin. So when you guys go into commercial production, is this still going to be a 3D printed part?
No, it would probably end up being injection molded, or even if it was more cost effective, you can make it out of aluminum.
Okay, got it. So you guys you did 3D printing just for the kind of rapid prototyping expedience of it. Okay, that all makes sense. Yeah, because this looks very much like it wants to be an injection molded part. If you've got the scale for that, and if not, then aluminum. Okay.
And then you have a more uniform cross-sectional area, and it's much easier to do justification work with that.
Make it thinner. Phosphorus.
Yeah. Okay. And the your solution was you're actually showing the solution in this picture was you just made it thicker and that solved the problem.
Yes.
Okay, great. And then the other thing I was putting out a little microfire, so I didn't quite catch it, but you guys did your endurance testing, and the part of it that I heard was that you stopped earlier than you wanted to.
On the double orbital test, we reached the 20-minute minimum threshold, and then we just called it quits. We didn't, because we had spent a long time getting double orbital working, and so this was right after we got double orbital working. We didn't want to push our luck, and also it was like we were in there for hours upon hours. We just wanted to hit the minimum threshold and then get out.
We probably could have made it longer than what we tested it at, but
yeah.
Okay, so it was this was more. So we try to. I'm actually having this conversation in Mech 2 right now with a student who's arguing with me about a PDR grade. And what I keep trying to write to the student is like Mech 2 and Mech 3 are like not about bean counting, right? Like that's not what we're doing, is trying to like make sure that you check every box. But in this case, we actually set, when I say we, I mean Alex, I'm looking at you. We set the testing time requirement, and you guys tested up to that requirement and then stopped. Is that okay? So had you kept going, where do you think it would have failed?
the pattern would have ended up getting out of sync at some point, possibly, or even the motor drivers over time.
Yeah, a lot of the code issues with the double orbital is just like a little, like you can see stutter in some older iterations of our code, just due to processing time on the Arduino. So probably with over time, it would probably come out of phase a little bit and lose that double orbital and become sort of like a clover maybe. That's what we saw at our first test. But I mean, it probably would have survived up until 55 minutes, but since we only tested up to 20, we can't be 100% sure.
And this test also came right after we did the 2 hours of orbital and then 55 minutes of linear, and had the linear failure, and reprinted a linkage. So we were in lab like 6 or 7 hours. Long day.
It was a marathon, yeah.
Got it. Okay, and so what I'm hearing is that the failure that you guys anticipate is not a mechanical failure, but almost like a software failure, or it could be
or electrical.
like the stepper motor doesn't count a step correctly or something like that, right? Or so that's actually not, I mean, okay, it's sort of catastrophic, but there's several ways to fix that, right? You could either specify a better controller that doesn't get behind in keeping up with the software, a faster controller. You could every hour or something like that just stop for a second and zero everything and then keep shaking, like after everything gets recalibrated, start shaking again. So you could do like a recalibration technique. So anyway, where I'm going with this is that they're, I mean, those really aren't like catastrophic failures, right? They're just sort of like, this is annoying. Where if you like beat this thing to death, like where would the mechanical failure be if it were to fail mechanically?
I would still put the mechanical failure at the 3D printed linkage arm.
Yeah.
It's the only 3D printed plastic part that is in the entire basis of the motor actuation system or linear slide system. These linear rails are actually relatively overbuilt for the size of the shaker table. They were just the most common linear rail size of this style on the market. So why spend more money for smaller rails when we could get, cheaper, larger ones that we know will withstand anything we throw at it. So really it comes down to those linkage arms.
Got it. Okay. And then you guys, you had another comment that piqued my interest about heat transfer and cooling, which we never get to talk about in design because we never pick energy thermal fluids projects, which makes me sad. But yeah, it was in there somewhere. It was as the motor drivers were overheating. So you say here, yeah, active cooling for motor drivers. So what does that mean?
I mean, so yeah, in our actual design, we didn't include fans. Like these motor drivers were getting insanely hot, like within a minute or two of running these motors. And that was fine for prototyping for the most part, but we did fry some motor drivers throughout that prototyping process. And once we got to endurance testing, obviously we couldn't, switch out a motor driver 3 minutes in every 3 minutes. So we brought in a pretty big fan. So in an actual design, this will need, I don't know if water cooling is, feasible, but definitely at least like a pretty fast fan and some good ventilation, because the motor drivers themselves they're just getting really hot running these motors at the speed.
Or
I also will say that our control box is external. It's not meant to be housed inside of a microbioreactor. So that will also help with the sort of cooling
yeah,
situation.
and it's possible that having better, we just pick, obviously we just pick the cheapest drivers and the cheapest, everything as low cost as possible. It's possible that better motor drivers would solve a lot of these, solve some of the speed issues, solve some of the RPM issues, solve some of the overheating issues. But we didn't explore that yet.
Got it. Okay. Yeah, sorry, the cat's here again. So, and of course she doesn't want to actually be shown on camera, but she also wants to sit on my computer. So anyway, sorry, I'm trying to manage her on the side here. Okay. Yeah. So yeah, I think, and Alex might be able to chime in on this a little bit, but the motor drivers, if you guys use the motor drivers that we've sort of been buying in bulk, those are basically the cheapest ones we can get. And so, yeah, I think a combination of better motor drivers, and I don't know that I would go as far as liquid cooling, right? That's every mechanical engineer's dream is to run liquid nitrogen through their gaming computer. And it actually, interestingly, it turns out liquid nitrogen isn't super good for that. It's very cold, but its heat capacity is almost nothing. But I like the idea that you guys things are falling off the table now. That you guys rolled in a fan and you were doing active convective cooling over your motor drivers. So intuitively that's precisely what I would have done. So you can imagine in the future, this thing is going to live in some sort of, when I say this thing, the controller is going to live in some sort of box, external, and you probably just have a really big fan and just blow environmental, ambient temperature air through as fast as you possibly can and take that heat away. What causes all of that heat? It's just you're driving the motors continuously.
Yeah. And then we're stepping them almost as fast as they can go, as fast as the code will allow them to go. And then we've got, they're not running with no load. They've got an entire shaker table to continuously shake. So, and we have the current turned up to max on the drivers themselves as well. So it's just a combination of all the above.
Yeah. Okay. Yeah. You're sort of running them right at the edge of where they want to be for long periods of time. So, okay. But the motors themselves don't get hot. It's the drivers.
Yeah, correct.
Okay. Okay. Yeah. So I think that's a solvable problem. It's like I said, a combination of better drivers and maybe active heat transfer in the control box in the future. So, okay, cool. All right. Well, now I'm all excited because we're talking about heat transfer stuff and I have all kinds of, other things to ask, but I'm also looking at the time and noticing that we're over. Oh, and then hang on, we've got, just for the benefit of the video, a comment from Javian in chat. Those drivers are the most basic stepper driver, really only produced for prototyping. They would never last a constant 2-week run. Laughter. So yeah. Okay. Yeah. So it seems like just a non-prototyping version of those chips those drivers will probably do that job for you. So, okay, cool. All right. So I'm going to stop asking heat transfer questions as much as I would love to continue, because we're now at the end of time. Are there any other questions or comments from any of the panelists before we wrap up?
Yeah, I just want to say one more thing. Throughout the many classes in the mechanical engineering curriculum that are project and group based, right? It's like everyone kind of dreads the initial judgment day of like finding out who your group is, right? Because everyone has horror stories of, oh, I was in this group and this person didn't do anything and I basically did all the work by myself. But you guys really seem like there wasn't that person, where everyone is kind of just on board with the same vision. And I wonder how many of the groups are going to all actually present in the same room. So far, it's only been one day. It's only been one day, but the groups that have gone so far have all been on their respective computers in different locations on Zoom. So I'm wondering who's going to actually show the true team camaraderie and present all together in the same place. So just props to you guys for really being a functional team.
Thank you.
Very good. Okay. Well, I think we've asked everything and said everything that we wanted to say. So we'll probably wrap it up there, especially because we're now about 4 or 5 minutes over, and I'm like physically unable to stop a class in time. So so sorry, I did it again for your presentation, but so just sort of final parting thoughts. So we appreciate all the time and effort and hard work that you guys put in this semester. Like I said, I really think this configuration is like the right one to move forward as a commercial product. So I'm excited for the coming semester in Mech 3. We're going to do the exact same thing that we did. We're going to basically give all of this semester's Mech 3 designs to that class of students and let them do house of quality and identify the best design. And I'm very hopeful that this one emerges for future iteration towards higher technology readiness level and eventual commercialization, because I really think that, it's just so simple and clean and elegant, and I don't know, it checks so many boxes for me. I love it. So just want to say that. And the other thing, if Dr. Nimi were here, he would congratulate you guys on surviving what many of our faculty colleagues call the final boss in the mechanical engineering curriculum. So we recognize that you guys basically go through hell this semester to get to this point. So congratulations on surviving that, and not only just surviving but also thriving and coming up with a really good design. And hopefully you guys had as much fun taking the class as we have teaching it, and you won't be strangers in the future when you're out in industry and grad school. You'll come back and perhaps serve as panelists or pop in and just say hello from time to time, because we're here and we love to see you guys even after you graduate. So
Thank you.
Thank you. Have a good afternoon.
very good. Okay, well, we'll see you guys later then. Let me hit the record stop button.